Really appreciate it. My name is Susie Shee. I'm an associate professor here in the School of Physics at the University of Melbourne, and I'd like to officially welcome you here tonight. I am the curator for the last 4 years of the July Lectures in Physics. Can you put your hand up if it's your first ever July Lectures in Physics? I'm actually curious. Lots, right? Thank you. Welcome. You're very, very welcome. We hold these lectures every year, every Friday in July. As you can tell, it is today, the 28th of June. I got a bit excited and jumped the gun this year. And our theme this year, it changes every year, our theme this year is physics and sustainability, which I think might have brought, some new faces to you. So you're very, very welcome. As a curator, every year I try to choose a theme that's topical and timely, and 2024 marks the first year of the UN's International Decade of Sciences for Sustainability. So I thought, perfect. What better topic than to explore how physics and sustainability intersect? So you're very welcome here this evening, and just before we pick the proceedings, I'd like to just acknowledge the traditional owners of the lands on which I work and on which we're enjoying this event this evening. That's the Wurundjeri people of the Kulin Nation, and just to recognise also the sustainable practices of First Nations people throughout 60,000 years of history. And so welcome and no respect to anyone from Indigenous populations and First Nations populations here tonight. You're very, very welcome. And it's really exciting to have everyone in the room. So before we kick off with our main lecture this evening, I actually have a special guest speaker for you. I'm not sure if you know, but the University of Melbourne has a fellowship program for students called the Watchel Fellows. And so I'll introduce who the speaker is in a moment, but just to give you a bit of background on the program and what's happening in the university in the sustainability space, I've just got a quick video first. That was not how that video was meant to go, so I'm going to skip it. Apologies, I'll post the video on the Eventbrite site if you'd like to watch it. And I have that fixed next week for those of you who come back every week. So the Watchel Fellows program, people apply to it from around the university, all different faculties. And through the program, they actually do a project and attend leadership sessions and events. And it's designed to get our students really engaged in leading sustainability in whatever that means to them in their practice. So we've had people develop dance performances and all sorts of things. And so for every one of the July lectures this evening, we actually also will have a quick mini lecture from one of the Watchel Fellows. So it gives me great pleasure this evening, before our main speaker, to introduce Alyssa Sefino-Crow, who is a student in science here at the University of Melbourne, studying mechanical engineering. And I don't think she needs any more introduction than that, because she's going to tell you all about the work that she's done. So over to you. Please make her very welcome.
Hello everyone. It's an absolute privilege to be able to speak to you here tonight as a young person and a student that's very passionate about the sea, and particularly the importance of bringing young people into this conversation, and specifically the way that we bring young people without making them feel pessimistic and overwhelmed about the situation of our ocean. So, many of you may know that our planet is covered by 71% sea, but what you might not know is the extent to which this impacts the health of our planet or what mysteries it hides below. So below the surface, you'll find a trench deeper than Mount Everest is tall. We know more about space. We know more about space than we do about the deep sea. The Greenland shark, which you can see up here, looks a little bit scary, can live up to 500 years old, which is the oldest being on planet Earth. And it breathes for us with every second breath we take coming from the sea. It has absorbed 93% of the heat generated by greenhouse gas since 1970. And without it, climate change would be so much worse. So for me, finding this out, I find it's very, very important that we learn about its impact on us. So let's get a quick show of hands. Who just learnt something new? Fantastic. That's great to see. That was the same for me. I had no idea about any of these things and how cool life below the water can be until I started the Wattle Fellowship 1 year ago and basically threw myself into everything related to the ocean. So I wanted to find out, I'm studying engineering, how could I actually have an impact right now rather than in 10 years' time where I probably have a bit more education around this field. So I had studied and learned quite a fair amount about climate change throughout my years, but I didn't know that it's actually the largest carbon sink on the planet, greater than all the rainforests combined, and I was really shocked by this because these basic facts aren't only becoming, they're slowly becoming known to the general population, with a majority of climate education focusing on land-based issues and many young people having very limited what's called marine literacy, basically knowing about what's going on in the sea. And one critical piece I wish I'd known back then was that there are many reasons to be hopeful, especially because the sea can actually regenerate very quickly, much quicker than on land. So, for example, giant kelp fronds can grow 45 centimetres a day, which is very quick. These facts and other things can help young people maintain hope in the face of climate change. So basically, a little bit about me. I grew up quite close to the beach here in Melbourne, and I loved the water and I loved sustainability. But throughout my schooling, as society became more aware of climate change, we got bombarded with a lot of scary facts and figures that I'm sure a lot of you have seen, and I kind of went from being hopeful and positive about sustainability to feeling very disempowered and kind of pessimistic. I just wanted to turn away and have nothing to do with it. And this isn't really what we want our young people to be doing. The defeatist response when becoming more aware about climate change is actually quite common among young people and is becoming more common, which is quite concerning. So rather than having the resilience to move past this fear, it's kind of like young people tend to see themselves as they want to work in sustainability and they put themselves in that group, or they just completely put their head in the sand, which we don't want. And because the sea is so large, some big topics like ocean acidification kind of seem too big for us to tackle, so I was like, what can I really do about it? So with a newfound passion to make my mission to teach young people ocean literacy and make it more inspiring and empowering, I developed a program called Young Ocean Innovators Program, and basically what this actually looked like was 6 weeks of intensive workshops with a range of different organisations and allowing experts and leaders in the field to talk to young people. But the bottom line was that it was solution focused. We got the young people to develop their own solutions, particularly for Port Phillip Bay and the problems that it faces. And we also went on a seal and dolphin swim with the kids to make sure that they get that hands-on experience and those memories that they'll keep forever, that remind them of why we need to protect our ocean and why we want to protect those dolphins as well. So it was absolutely fantastic to work with young people, see them present their solutions. We had some students designing a robot that can pick up microplastics on the beach, to teaming up with diving companies to collect sea urchins that were causing a heap of sea urchin barrens in Port Phillip Bay. And I'm currently planning a Young Ocean Summit and hackathon for university students at the end of the year to make sure that we bring them into this discussion as well in a positive way rather than focusing on the negative statistics. So also with the Wattle Fellowship, it's been a fantastic year, and seeing over 20 other projects from young people in all different faculties actually come to life has been absolutely amazing, and I've made some lifelong friends. So I hope you've learned a little bit more about the sea and why it's so amazing, but I'm sure you'll learn a lot more from Dr. Navid, and maybe you feel a bit inspired about how you can think outside the box and take small actions to make young people around you feel like there is hope for them and there is a reason for them to take action right now. Thank you.
What a wonderful project, and actually I think it's so wonderful to hear from our own students in this lecture series and not just us rapidly ageing folk. Right, so to our main event, our main speaker tonight Navid Constantinou. He grew up in Cyprus and studied at first in Athens, getting his PhD in 2015. He's been awarded a number of prestigious postdocs. He's worked at the University of California, San Diego, and he first moved to Australia in 2018, first to work at the institution that will not be named, Australian National University. Joke, it's not really that much of a rivalry, honestly. But we are incredibly pleased to now welcome Navid as one of our own staff here at the University of Melbourne, because just in June 2024, so I've nabbed him in his first month with us, he's joined the School of Geography, Earth and Atmospheric Sciences here. And tonight he's going to be giving a talk about, as you all know, oceans in motion, and as an oceanographer, how his work relates to climate and to climate change. Navid,
thank you.
Over to you.
Thank you very much. Okay, now is where the technology will fail or something. All right, let's see. Let's do this back. All right. Okay, I set it in motion. Hi, thanks for having me. It's a great pleasure to talk to. This is the biggest audience I've ever talked to. Just saying, yeah. I'm going to talk to you about oceans, and I'm going to talk to you about all the mesmerising patterns that the ocean circulation forms. Look at this. What we see here is an animation of the North Atlantic. We see the Gulf Stream starting from Cuba or the Gulf of Mexico and bringing warm water up to the UK, making it a little bit more habitable. And you see that it's not just coming in a straight line, it's all these circular features, all these turbulence that comes with it. And that's what I'll try to show you and take you through the journey, in case you haven't seen these things before. So, first, to put some things in perspective, it's okay. What do we study the ocean? It's quite a big part of Earth. It's actually whatever 70% or something. So it's a big part of the Earth system, the ocean, and we are Earth creatures. So we are, land creatures. So we are kind of focused on land sometimes. Narrow-minded, but ocean is a big part of the climate system, so that's one reason to study it. I'll give you more. So, when people usually think of the ocean or the motions of the ocean, when I talk outside the university, people think of waves, the waves, the wavy ocean, and that is kind of quiet and beneath the waves. And here's some, these are pretty rough waves in the Southern Ocean. This is one of the most wild seas you can be. Looking at this video, I'm really happy that I'm not a seagoing oceanographer, but that's not where I go to work. I go to work at my office, in the comfort of my office. And but that's how the ocean looks like on the surface. But what we're looking at here is just the tip of the ocean, the tip of the iceberg. If we go beneath the waves, we'll see much more interesting, to me at least, and intricate flow features. So that's what I'll take you to tonight. So, a little bit about what will happen tonight. I'll show you how ocean motions look like, and then I'll talk a little bit about what sets these motions, what drives these motions. What is this sound?
It's your microphone.
Good sound.
It's your microphone.
All right, we're swapping up. Yes. So now it's unmuted. Here we are.
Unmuted for you, so test this one.
Oh.
Sorry. Maybe up a little further from your end.
How do you hear me now? Yeah? Alright, good, thanks. That's great. So I'll talk to you about what drives these ocean motions. then how the ocean has been changing, the past, post-industrial revolution, and a little bit on ocean and climate. Right? So let's go. Okay, so first a little bit of basics of climate science. Or why is the ocean in motion and the atmosphere? So what happens is that the sun shines at the tropics, and then somehow this energy that gets into the tropics has to move towards the pole, and then it gets radiated out. Because if it doesn't, then we would have boiling water in the tropics, and we know that is not the case. So both the ocean and the atmosphere, and this is a quite simplistic view, but both the ocean and the atmosphere transfer some of this heat towards the poles, where it gets radiated out. Okay, it also gets radiated out elsewhere, but that's like a basic of what's happening. And this movement is what sets the atmosphere and the ocean in motion. So if what comes in is exactly what goes out, then we have a steady climate or a climate in equilibrium. We don't have climate change, we're all good. Okay. If there's a little bit left over, and what comes in is not exactly what goes out, but there's a little teeny weeny leftover that comes back in, this little purple thing here, then that accumulates over time, and we have climate change. And we are talking, and this is really climate change, this little teeny weeny purple thing. And if we put some numbers onto this, instantaneously on the sunny day, on the sunny summer's day, we may be getting 1,000 watts per meter square at the surface. I don't even have any intuition of what that number means, but if we compare it with the climate change signal, that's 3 to 5. So it's a really, really small residual. Okay, that's what climate change is. But if you add this up for 80 years, or how many years you'll be doing it, then you get 1.5 degrees warming, you get floods, you get whatever you see in the news. I don't want to, bring people's mood down, but you get all this. All right. So now it was already mentioned that so there's this big pompous committee. It's called the Intergovernmental Panel on Climate Change. It's a big bunch of scientists from all over the world. They form a committee and they write reports, and they give it to all governments, and they suggest what they should be doing. Some follow it, some they don't. So this committee is called IPCC. I'll try not to use acronyms, but this is quite a known one. So it's called the IPCC. So in their last report, they have this figure, which we see here. All this excess heat that we have put in the system due to climate change, this little teeny weeny purple thing that stays in, how much has gone where? And this is the total amount of heat that is in the system with this uncertainty. And this is in the ocean. This is in the ocean also. This is in the ocean. The ocean has 3 bits here. I don't know why. So big that they couldn't put it in one. It would be like, it would look terrifying. So all this is ocean, and then there's something a little bit in the ice, some in the land, and you see this is the atmosphere here. Like, I don't know, you may think this is the thickness of the line at the bottom. There's something there. So 80 to 90% of the heat that we have somehow made the system have more, the excess heat, is in the ocean. So the ocean acts like a damper. It's taking all the heat, and for us land creatures, it's quite good because we are experiencing only this little bit here. What goes into land and in the atmosphere. So the ocean is really a saver here, and it's quite important to understand the ocean because if the ocean decides to do not to do 80 but to do 70, that would be a lot more for us outside the ocean. Okay. So now what happens in the climate system in general? All this heat that comes in from the sun doesn't go only in the ocean, it goes in the ocean, in the atmosphere, clouds, trees, ice, and whatnot. And everything exchange energy and momentum. All these things are really intimately connected. And after all the exchanges happen and everything happens, then energy radiates out to space, and we are left with this teeny whiny residual. So all these things are intimately connected, and that's why it's kind of like hard and complicated, and we haven't able to solve this kind of problem yet. I mean, this could be the start of a lecture, of the whole lecture series. So I'm not going to go into that. I'm going to talk about the ocean today. Okay, so how is the ocean moving this heat around, and how does the ocean motions look like? Okay, all right. So here I want to show you how the ocean looks today. So I'll go to this website. This is where things break. All right. Okay. Now let's click here. This is how the atmosphere looks today. Okay, let's go up in this height. This is the altitude where airplanes fly. So you see, this is how the atmosphere looks. It's not, it's not straightforward, but it has a lot of this. You see all these circular features. There's like one eddy here, another one, another one, all these big circular features, similar to the ocean. There's one here, okay. Now, all right, enough about the atmosphere. Let's go to my favorite place. Okay, let's go to the ocean. That's how the ocean looks today. Okay, this is a quite dangerous website. By the way, I had it as a homepage at some point, and I was losing 1 hour a day looking at this. So you see, currents like that, and full of these circular features. These are what we call eddies. This is turbulence, ocean turbulence, like the atmosphere, but much, much smaller. Okay. Now here, this is the East Australian current. That's where Nemo lives. Or no, Nemo lives at the coral reef, but they took the East Australian current to go find its dad. We see here the Gulf Stream again. We see this big river of water, and all these circular features accompanying it, and and we can lose here all day. And you can see here, this is another one favorite of mine. There is a big current that goes around Antarctica. That's the biggest current in the ocean. Anyway, so that's how the ocean looks like today, and I think I tried to convince you that you see a lot of these circular features, okay, both in the atmosphere and in the ocean. And where do they come about? Let's see, what's the next slide? Okay, yes, this. So I want to, they come about because we live in a rotating planet. Okay, so it's living in a fluid environment that is rotating is what gives rise to all these circular features. And I would like to demonstrate that now. And this is where, again, things break down, because this works when nobody is here. And then when 5-10 people come, it's not working anymore. But let's see. So can somebody help me from the audience? Just to hold the hold the phone.
Do you want to volunteer? Would you like to volunteer, sir?
Let's see.
There you go.
All right. So just let's see. Video, and you just hold it here. All right. This is non-rotating. You can see it. Yes, you can see it. So I'll stir it up a little bit, and I'll put some dye in, and it should look similar to when you put milk in your coffee. All right. Nothing too exciting. And it's fascinating, but yeah, that's it. All right. The milk has now been stirred up. All right. Okay. Thank you very much for your help. This was great. Now we have here our rotating planet. Let's see if this works. Okay. And I put my phone on it, so now we are in rotating with it as we are here on Earth. We don't go to space and watch Earth. We are on it and watch the weather. So this has been rotating for a bit. And I'll do the same thing. Give it a little steer and put some dye in and see how the flow looks like. And you see they don't mix up very well. And you see already some circular patterns forming. Please form. Yeah, I mean, I see it. I don't know if I see it because I want to see it. But first of all, if you see it here, it looks really different than this one. This is like all mixed up. This is not. So, you see a vortex there? Yeah, okay, that's a vortex. That's an eddy. That's a turbulent eddy. That's a low pressure system. You may see. So, yeah, so rotation gives the tendency of the fluids to form these circular features. And now I'll stop it. We will. Oh, this is also interesting what's happening here. But anyway, I'm stopping it. And yeah, that's it. That was the demo. All right. It worked. I don't know how. Okay. Oh, this was the video in case the demo didn't work. All right. It's a video from my not to name previous institution, but anyway, I'm moving on. We're moving on. Okay, so how do we model the atmosphere and the ocean? So we take the atmosphere and the ocean, we split it into little boxes like that, okay? The smaller the boxes, the better. And then we apply Newton's law of motion in every of these boxes, okay? It's nothing more complicated than that. It's just a lot of boxes, usually, because you want to make these boxes as small as possible. So it's a lot of boxes, like we're talking millions of boxes. So we can't do it by hand, and we put it in these supercomputers, which is like having 100,000, 60 laptops connected in series. But that's how we do it. All right, it's a lot of computational effort. A lot of the biggest supercomputers in the world are devoted in running climate models and Bitcoin also, and and AI training now. But climate models still a lot of them climate models. I lost this thing that here it is. All right. Now, and this is I think this is the last equation we'll see. Okay, so don't get intimidated. We saw another one before, but that's another equation. All right, so I'll show you now how the ocean looks like. So this is a movie from the biggest ocean simulation ever run, with the smallest boxes ever possible. So this is a box that on its side it's 1/48 of a degree, and because that means nothing to most people, even to me, it's like 1 or 2 kilometers. Every box is 1 kilometer wide. Anything smaller than that, it's invisible to this body. And still, you'll see all these details that you will about to see. What are we? We're looking here at the North Atlantic again. When you see light colors, it means the ocean moves faster. So this is the Gulf Stream. And let's get this rolling. So, all right. So you see these things here are tides. Tides go in, out, in, out, in, out. You see eddies. You see waves emanating and propagating all through the Pacific Ocean. It's like you have to squint your eyes a little bit. I've seen this many times. I spend my afternoons looking at this thing. You see the East Australian Current, again full of eddies. You see tides here, strong tides here in the north of Darwin. You see this current that goes around Antarctica. You see another current here, another big current. It's called the Agulhas Current. It brings warm water from the Indian Ocean down to the tip of South Africa. So, as an oceanographer or climate scientist, we need to understand all this perplexity of motions together. You can't understand just one, like let's understand the Gulf Stream ignoring the eddies, or let's understand the waves, ignoring it's unfortunately they are all intimately very connected. Also, mind you, the ocean is three-dimensional. I'm only showing you the surface here, so there's a three-dimensional aspect to that, and it gets so that's why we need help to study these things and understand it, and understand how it affects climate. Let's talk a little bit about what sets all these things in motion. All right. Okay, so first of all, if the main driver of the ocean circulation are winds, all right? Like the wind blows, kind of intuitive you would think, okay, the wind blows at the surface of the ocean, it carries water with it, and then you have circulation, all right? The other main thing that drives ocean motions is the moon, because the moon creates the tides. Okay, and I'll go a little bit in detail in a little bit about that, because there's more to tides that one meets the eye. And then there's everything else. Everything else, this 1% here may be an exaggeration, but there's like the heating from the surface, like volcanoes at the bottom of the ocean. Some people have like put forward that the whales moving are causing things to mix, but we can think of winds and tides as a very, very good approximation of what drives the ocean. Here's how the winds look like. This is how the winds look like at the surface of the ocean if you take an average of June, July, August, or December, January, February. So you see that the winds have very distinct patterns. There's like all these winds that blow from west to east in the Southern Ocean, for example. Ooh, that was a lot. Don't know what happened. Yeah. All right. And there's like these winds that blow from east to west. It's called the trade winds. You can see them in the tropics. But then if you compare how the mean winds are and the mean ocean circulation, look here, I've taken the ocean circulation and removed all the interesting bits. All these little wiggles and whatnot, because otherwise you won't see anything. So this is like a schematic of how the circulation looks like. This is how we learn about the Gulf Stream first, and that's why we think it's a straight line, for example, that goes. But you've seen it's much more complicated than that. But if we take out all the little details away, and we keep the rasa, or the essence of the ocean circulation, that's how it looked like. So it's more or less very, following the winds. There's this current around Antarctica. There's the Agulhas current that brings water down to the tip of South Africa, the Malvinas current. There's a current here in the coast of Japan. Yeah. But I want to show you, now if we put the details back in, all right? There's something else that happens, generally in turbulent fluids, that turbulence comes in many scales. So we see here, this is the tip of South Africa. This is the same picture as I was showing before. This is colored now with blue and red, depending on where the flow has a tendency to rotate. We call this vorticity, but forget about that. It's just a nice coloring to see how the ocean looks like. And you see, what you can notice here is that there's some eddies. For example, this is one eddy here. And there's some eddies inside the eddy. And even here, there's a lot of 3 blue little eddies inside the eddy. So there's like, it's like a fractal thing, that the more you zoom in, the more you see. Okay, this is quite mesmerizing. I was trying to make my lecture yesterday. I was ending up looking at this for 2-3 hours. So, you see this eddy, and then there's eddies inside the eddy that form, or here you see this blue eddy, and then there's little eddies that shed off this blue eddy. It's like, it's never ending. And it's not just beautiful details, unfortunately. All these little small scale things matter for how the big, large scale circulation is formed, and then how this heat and how much of this heat is transferred to the poles, how much heat is absorbed from the atmosphere into the ocean, and whatnot. So it's not just for the artistic, it's not just for movies. that they are important. They are actually important for heat transfer, heat absorption from the atmosphere to the ocean, carbon absorption, and whatnot. So at some point, I guess we have to stop it. Well, all right, I can pause this and we can have a look, all evening, or put it as a screensaver. Okay, now how about what the moon does? All right, we know the moon is responsible for the tides. If you've been to the ocean, here, the Southern Ocean, in Great Ocean Road, you notice that there's tides, strong tides, twice a day, more or less. So, how does that work? Okay, so let's take, I get this question a lot, the question I get is, the moon goes around the Earth once a day, but why there's two tides a day? So I'll take this opportunity to explain a little bit. So if we have this, the very simple version of the Earth and with only water here, and it's quite exaggerated here, because the ocean is around 4, 5, 10 kilometers top deep, while the Earth radius is like 6,400 kilometers. So that's a big exaggeration here, but it's just for visualization purposes. So if we had a word like that, which reminds of the Doomsday movie, if you've seen it, but anyway, and we have the moon here, one would expect that, all right, the moon has its own gravity. It's a big object. It has its own gravity, so it can pull the water that is close to it and create something like that. It will make the ocean look like that, all right? And then if we have somebody standing there, and then as the Earth rotates, then this person will go through this bit once a day. So 1 tide per day. Wrong. Okay, that's the wrong thinking, but that's the intuition that most people have. Why it's wrong is because we kind of forget some bits of the story. So the moon's gravity pulls everything, not just this. It's not really selective. It's not discriminatory. So it pulls this bit of the water. It also pulls the Earth, but a little bit less. You mean this arrow is a little bit smaller than this because the Earth is a little bit further away. Okay. It also pulls this bit of the water, but also less because it's even further away. It also pulls these bits of the ocean, but in an angle. So when you put all these things together, you get the 2 boundaries. All right. So then now, when the person sits there and as the Earth rotates, they'll feel 2 tides per day, which is the right thing to do. All right. So that's the explanation for that. So as we are here, for example, we are in a low tide situation. We say the tide comes in, as we go there, then it goes out, comes in, it goes out, and you get the picture. All right. So what we see here is this oscillation. All right. That's what we experience. I don't know how many slides did I put here. Okay. You got the idea, right? All right. So there's this debate between these 2 people in American TV. I don't know if you've seen it, but one of the argumentations trying to make sense that like we have to take some things for granted. We don't need to prove anything. This person said, "Oh, tide goes in, tide goes out. You can't explain that." And I mean, it was kind of the worst example they could give because actually Newton explained that 400 years ago with the theory of gravity, and we actually know how to. Not only we know how tides work, we can actually predict them very well. You can go in the beginning of the year and buy tide calendars, and they can tell you when it will be high tide on 25th of November, 11 months from now. So that was quite funny. But anyway, I don't know how many oceanographers watched this show and got that. But this is not the type of motions, what I was showing you before, is not the type of motions that the tides create. The tides create this sloshing in and out, but then there's more to that. Now, imagine we have an ocean which is stratified, as we say. It's like lighter fluid at the top, lighter because it's a bit warmer at the top, or a bit fresher, not so salty, and then denser at the bottom. Denser because it's a bit colder at the bottom, and saltier. Okay, salt makes water a bit more dense. So then if we have this thing, and then we have this tidal oscillation, this tide goes in, tide goes out type of situation, and we have a little mountain at the bottom of the ocean, and we have plenty at the bottom of the ocean. Then what will happens is that this thing happens. And all this motion here and all these wiggles are indirectly related to the mood, because the mood creates the oscillation, but because then we are forcing the whole ocean to move above the mountains at the bottom of the ocean, all these motions are created. And this is the tidal motions that the moon is responsible about. To give you a more better perspective on that, for example, these motions were included in this big animation that I was showing before. It's part of the cage. Now, some people took an ocean model and somehow carefully turned everything else off. There's no winds, there's nothing else in this model. They start from an ocean at rest, a quiescent ocean, and they only have tides. And then they let it go. And after a while, you'll see that there's motions everywhere. And it's this type of motions that originate from mountains at the bottom of the sea. You see there's a lot of things happening where Hawaii is, a lot of things happening where Tahiti is, a lot of things happening in between this, because there's a big mountain range, underwater mountain range, in the middle of the Atlantic Ridge. In the middle of the Atlantic, it's called the Atlantic Ridge. So you see all this chaos just comes from the tides, from these type of motions. Like the moon forces the ocean to slosh around bathymetric features. Yes, 10 minutes, great. All right. All right, I want to talk to you a little bit about how the ocean is changing now that we have kind of like seen how the ocean has been moving. And yeah, all right. So how do we monitor, first of all, the ocean's temperature? So one way is satellites. Satellites are flying all over us, and they monitor a lot of things. One of these is the ocean's surface temperature. Okay, there's other ways to monitor these things. The ships that go around, research ships or normal ships with monitors on them, or there's these self-propelled floats that these are quite interesting piece of equipment. They float down. They go down at 1,000 meters deep. They float with the ocean currents. They measure things, and then they rise up and they send their measurements to the satellite, and they do it again. And they are all over the ocean. But anyway, mostly with satellites, what I will show you now. So here's what the mean sea surface temperature looks like. Okay, it's warmer at the tropics and colder as you go to the poles. Now, because we have a long satellite record for 30, 40 years now, we can go at each point and see how the temperature has been evolving. And then say, compute if at each point has the temperature been rising or getting cooler, all right? And here's that. So when you see red, it means at that point the temperature has been rising. When you see blue, it means it has been becoming cooler. So more or less it's everywhere red, more or less. There are some places that is really red. This is like 1 degree per decade. This is the Gulf Stream region, or the region of the Kuroshio Current, or the region of the Malvinas Current. You see the regions where eddies are more prominent are those regions that the ocean is getting warmer. When you average everything out, we get to about 0.1 degree per decade. That's quite significant. And yet, the ocean has been warming up. Warmer ocean means more evaporation, more clouds in the atmosphere, more rainfall, more hurricanes, more floods, more whatnot, everything you get in the news. But yeah, that's it. So now that's about the temperature. How are the motions of the ocean measured? So again, with satellites, different satellites, we can measure the sea surface elevation with very, very good accuracy, up to centimeter accuracy. And then, from the sea surface elevation, we can use Newton's law of motion and the equations of motion, and we can infer the surface ocean currents. Okay, that's a quite straightforward thing to do. And we can do that. And this is a map of the energy or the speed of the ocean circulation. You see the ocean is more energetic where you have these strong currents, the Gulf Stream, the Kuroshio current, this current around Antarctica, the Malvinas current, Nemo here, the East Australian current. And now we can also do the same exercise. Go up the satellite network and see every point, has it been speeding up or slowing down, right? So blue means it's been slowing down, red means it's been speeding up. So there's a lot of points, especially the regions where the ocean moves fast and there's a lot of energy in the ocean, it's been speeding up. Okay, here also. So the ocean is changing. That's my main takeaway from here. Now I want to touch a little bit of okay, do we care, or is it just like the ocean, and then what happens in the ocean stays in the ocean? No, the ocean interacts quite a bit with the whole planet. And I'll give you here only one example, something that you probably are familiar with, because when it happens, it's all over the news in Australia. Either when we have El Nino or La Nina, this is this, collectively we call this El Nino Southern Oscillation. When we have El Nino, it's a phenomenon that it's intimately connected between the ocean and the atmosphere. We have that the ocean in the East Pacific gets a little bit warmer, and then the atmospheric, and then there's like much more evaporation in the atmosphere, much more rain in California. How do you say the opposite of rain? I forgot the word. I don't know, like drought. Okay. Drought in Australia, fires and whatnot. And when we have La Nina, it's the opposite. Somehow the ocean creates a colder patch in the East Pacific, warmer patch in the Philippine side. We have evaporation, more evaporation in the atmosphere. And on this side, we get all the rain, the floods, and whatnot. News in both ways, not things that we are excited to get. And if we go back to this picture, as we said, the ocean has been taking almost 80 to 90% of this extra heat. So small changes in the ocean could mean a lot for land creatures, because if the ocean decides somehow, because it's not like I don't want to anthropomorphize, but if the ocean somehow by changes, instead of 80 decides to take 70, then there's 10% more for these bits, but that's like double. So we would be experiencing double what we've been experiencing now. So small changes in the ocean means a lot for creatures in the atmosphere and land. Something to take home is that the ocean is beautiful. If you were going to take one thing home, just take that. Don't take the other bits. Yeah, the ocean is beautiful. It creates all these beautiful turbulent patterns. So it captures 90% of the heat that we've been producing. So it's helping us a lot. It's doing a good job for us. And we would like to study better, because if small changes in the ocean circulation can induce big ramifications for the heat or CO2 that is left in the atmosphere for us to experience. And also it can bring a lot of changes in global and regional climate patterns. And I'll leave you with this photo. This is a photo I took near where I was living before. And it's quite cute, I think, but also a bit angry, I think. And I think it's mostly angry because not as many people study the ocean. So you should come join us. It's good fun, it's for good cause. And I'll be outside taking registrations for our courses, our classes, our PhD programs, whatever you want to contribute or learn, we're here for you. All right, thank you.
All right, so just get these going.
Great audience.
Great fun, aren't they? It's question time, both.
wow.
So, can you pop up your hand if you have questions? We've got 7-8 minutes for questions, I think. So, Barley, can you take this here? And I'll come to you next, please.
Thank you very much, David. That was very interesting. I appreciate this points about society. I have a question on the science there.
I can hear you appreciate the points.
The points about the broad society.
All right.
Could you go back to the trends in speeds of the currents?
Yeah. Oh, wow. That's the here.
Yeah. So, being cease of current, cease of. Can you explain between the top and the bottom? Because you said the surface currents are speeding up, but I see a lot of blue, like at the Gulf Stream, for example, where it's a strong current.
There is blue and there's a lot of red here also.
So, how can we make sense of that then?
Well, you can make sense because also, I didn't want to go into these details, but thanks for asking. Because the current is also shifting a little bit. So that's why, because the current is shifting and it's going northward, I think, that's why you get a little bit blue left over here where the current used to be, and you get more red where the current now goes. So this shift is part of the, I think, I don't want to write this in stone, but it's part of the shift in wind patterns that also occur with climate change. So that's there's more, you have to go into more details to understand what sort of changes created this pattern here, whether it's the eddies that are speeding up, the currents that are speeding up, we have more eddies, but of the same strength, or we have the same number of eddies, but they're speeding up faster, these kind of things. Yeah, we have to get into the nitty-gritty details, but I think what you're seeing here is mostly the current shift. Thank you.
Thank you for the very wonderful talk. I had a question too, actually, and maybe they're related. So for like the sources for the motion in the ocean, does the Earth's rotation have anything to do with that?
The Earth's rotation doesn't create motions, but as I've shown you here, hopefully, the Earth's rotation shapes the motion, shapes what sort of motions and what sort of type of eddies will be produced. So it's the Earth's rotation by itself does not put energy into the system. That's what I mean. It doesn't create motion by itself, but then if you put energy in the system from winds or from whatever, from sloshing around with your balloon, then the Earth's rotation will dictate of what sort of flow patterns you will see. And all these eddies and all these mesmerizing pictures that I was showing you, you wouldn't see if the Earth was not rotating.
And so
most of them you wouldn't see. Sorry.
When you showed the pictures of the currents, I saw one that was made like on the equator. You see this current along the whole equator. Well,
Yeah.
Do you know how that works?
Well, here, for example, and also in the Pacific, yes, that's so the Earth. So the Earth's rotation. I'm trying to explain it now without getting too technical, because then we won't get the registrations for all our So there's like an apparent force that the ocean and any fluid feels because of the Earth's rotation, and that's called the Coriolis force. And that's because the Earth is spherical also. And this force changes sign exactly at the equator. Okay, perhaps you've heard it before, perhaps people are saying, oh, you go down to Australia and then, things will be flowing the other way around in the toilet, things like that. That's not really true. For this type of sizes, we don't feel the Earth's rotation, unless you put it on a rotating thing and leave it for half an hour. But because this Earth's rotation, this Coriolis effect changes sign here, then the equator acts a little bit like a barrier. So that's why you see this sort of motions here and in the Pacific also. There's like different type of dynamics that act in the tropics compared to the mid-latitudes. So that's part of our, courses carried in Japan.
More questions here? I think there's one at the center. Oh, you got it. Yeah. Behind, I think.
You only mentioned salinity very, very briefly. catastrophic melting of the Greenland and Antarctic ice caps did come true and what effect that might have.
Yes, all right, I can get into that a little bit. So, to really understand what the effect of that would be, you have to think about the three-dimensionality of the ocean. So, alongside with this sort of like motions that take heat from here and take it up to the North Europe, for example, and then bring them down somehow. There's also a motion of the ocean that takes water from the south part of the Atlantic, brings it up and brings it up to the north, to the Arctic, and then that water dives down. You cannot see it because you have to go, it's three-dimensional, you have to go, it dives down and then sinks down. That's also a big part of how the ocean transfers heat to the poles. And if we pour a lot of fresh water here, or a lot of fresh water in Antarctica, then we might disrupt that bit of the circulation, and that thing might collapse or tear down, and this is what sometimes you see in the news, the collapse of the overturning circulation. That's what they mean, that's the natural current. It's a speculation still. I mean, we see it happening in models, but we're not sure if we are 1 week before that or 10 minutes before that. Don't get too try to sleep well. But that's I think that's a bit you're referring to, right? Was this answering your question? Did this answer your question? Right. Thanks.
There was one here.
Thank you. So I just wanted to hear your thoughts, if you had any, on how, whilst the ocean is important heat sink, and the fact that it's delayed the upcoming kind of crisis for us.
I'm sorry, I didn't hear it. Whilst the ocean is important heat sink, then?
It's not an unlimited heat sink.
Yes. It's not unlimited. I don't know if it's limited, but yes. True, it's not unlimited. And also, I mean, although for us land creatures, put that in the ocean. It's like putting it under the rock. It does matter. Putting carbon in the ocean, heating the ocean changes, how corals are, what corals experience, or ocean acidification, all that thing. It's true that it's not limited. I'm not in a position to quantify how much more it can do it. I don't know, to put numbers on that. I'm sorry, but
I just wanted to hear your thoughts.
And
then I was just also wondering, I found it interesting the two graphs you had where we modeled the speed and then also it was the heat, I think.
Temperature.
I was just wondering, when you show that, do we have any modeling of solar radiation as it falls across the Earth and the impact that
So that was not, you're talking about this, so now I have to go through the whole thing again. All right. You're talking about this and the next one?
Yeah, and
this
so
one.
I'm just interested in how solar radiation falling across the Earth and how that would map to these two graphs as well.
All right, I see what you mean. But by the way, this is not models. These are just satellite measurements. In practice, they have included everything. But you're talking about, say, for example, if I understand your question correctly, you're saying, okay, here is where, the ocean has been heating up, for example, a lot. Do we get a lot of solar radiation here?
Less clouds or something. Right?
Yeah, well, we actually get more solar radiation in the tropics or something. I think you will get even less solar radiation there. So I think that heating up is most, I don't want to make it call that, but I think it's mostly because the ocean somehow, both the ocean and the atmosphere are transferring more heat towards the latitude, and that's what the ocean is experiencing. If I had to guess now, it's a guess, I would say that it's not because the solar radiation here is being increasing. I think it's because the atmospheric and the ocean circulation are such so that they bring more heat there.
But the wonderful thing about our setup tonight is that there are going to be some drinks and meals out in the foyer. A little bit of housekeeping. There is, as Mules has said on the way, the Melbourne School of Design exhibition, which was on the party last week. But there will see some students' work displayed out in the foyer, so I just ask you to be a bit careful of that. Some of it is quite fragile, but I would like us physicists to, or physics interest folks, to be going toward ruining our architecture students' lovely work. So, as you know, your drinks, please just mind elbows and things. So, thank you all for coming tonight. First of all, let's give an amazing big round of applause. And also, of course, to our students who are here earlier this evening, Elizabeth. Thank you. This is the largest audience he's ever spoken to, so imagine speaking to an audience the size of this student. You did brilliantly. You have a very bold future ahead of you. So, for those of you who are registered for this series, you know that we have 3 more July lectures this year, and next week's is given by Julian O'Shea, who some of you may know from YouTube and TikTok, a bit of a superstar on there, but he's actually Dr. Julian O'Shea, and he does research in sustainable transport. So that's going to be an interesting one next week, so please do come along. And in the meantime, in a moment, once we've packed up, we will join you out in the foyer for a drink, and you can continue to ask Louis and Elizabeth questions. So thank you all for coming, and have a